Hello everyone, my name is Mao Yanchan. I'm a fifth-year PhD student at National University of Singapore. Today, I will introduce StreamOps, cloud-native stream processing runtime management in ByteDance. This work is done when I was an intern at ByteDance. Let's first see the stream processing scenarios in ByteDance. ByteDance applications rely heavily on stream processing to handle massive amounts of real-time streaming data. Specifically, these applications serve 1.9 billion users across 150 countries and regions, and millions of recommendation requests can be generated and need to be processed in real time. Streaming services in ByteDance typically show three key features. First, large-scale deployment. There are 40K Flink streaming jobs deployed globally, and they are allocated with 4 million CPU cores, and 18K jobs are enabled checkpoint with a peak throughput of 600 gigabytes per second. And these streaming services may process up to 9 billion of queries per second. Second, stream processing is widely adopted for diverse scenarios. For example, real-time feature extraction, real-time model training, real-time data warehousing, and security and risk control. Streaming jobs under different scenarios have diverse input workload characteristics and performance requirements. Third, workloads and resources may change over time. Specifically, the peak input rate can be 4 to 5 times higher than trough input rate. And unexpected exceptions may arise during data processing, and tasks of streaming jobs can be deployed on slow machines with limited computational resources. And normal machines may also slow down the streaming job if deployed with too many tasks. These changes of workloads and resources causes varying runtime issues such as processing lag, runtime failures, and resource wastage. As a result, a cluster-wide runtime management platform is needed to manage streaming services in ByteDance Cloud. A Flink streaming job will be running in a Flink runtime, and it will be deployed as a set of parallel tasks that form a physical execution topology. The runtime management service is typically a control plane that periodically reads the runtime status of streaming jobs. Then it explores optimization opportunities for streaming jobs, and then dynamically reconfigure these streaming jobs accordingly. By summarizing stream processing features, the control plane in ByteDance need to have three main requirements. First, the control plane has to be scalable enough to manage 40K streaming jobs in ByteDance Cloud. Second, the control plane should incorporate effective control policies to address common runtime issues such as processing lags and failures. Third, it should be extensible to design new control policies and customize them for diverse stream processing scenarios. To achieve all these requirements, we need to make appropriate design choices according to ByteDance scenario. By summarizing existing research and industrial solutions, we found there are mainly three design decisions to be made. First, where to deploy the control plane. Second, how does the control plane apply cluster-wide runtime management? And third, where to store the runtime management state. For the first question, the control plane can be either, first, deployed as a spatial control operator in a streaming job topology, or second, as a centralized service inside the streaming job, running alongside the job master, or third, as a standalone service running outside of streaming runtime. The first two choices achieve low latency and efficient interaction between control plane and streaming runtime, but requires significant modification on the streaming engine source code. In contrast, the standalone control plane decouples the management of streaming engine and control plane service but at the cost of remote communication cost. Since the streaming jobs are largely deployed on ByteDance Cloud, we need to avoid ending engine-level maintenance overhead. To this end, we choose standalone control plane for its independent development and lifecycle management without modifying streaming engine source code. For how does the control plane apply cluster-wide runtime management? In particular, there will be multiple control plane instances working cooperatively. Control plane instances can either, first, scan the cluster-wide streaming jobs proactively, or second, receive runtime management requests triggered by streaming jobs passively. In the former design, streaming jobs can be managed without awareness of control plane instances, but it limits the functionality to customize the runtime management frequencies for different streaming jobs. The latter design enables more customizable runtime management for each streaming job, but requires to manage an additional trigger for each streaming job. Since we have diverse stream processing scenarios and they require more customizability, we eventually choose the passive per job triggering to customize and fine-tune runtime management strategies for varying stream processing scenarios in ByteDance. The proactive cluster-wide scanning can also be achieved in passive per job triggering by configuring a centralized coordinator to trigger runtime requests for all streaming jobs. The runtime management of streaming jobs can be stateful. For example, control plane need to read historical metrics to make appropriate runtime optimizations. So the next question is where to store the runtime management state. There are generally two options. First, store state locally on each control plane instance. And second, store state globally on some storage services. The former choice enables efficient state access, but requires additional state management overhead on control plane, while the latter choice makes control plane instances stateless and more scalable. We eventually choose global state store to make the control plane service stateless and lightweight. It can also reuse existing in-production storage service in ByteDance for state store. We combine all our design decisions and then develop StreamOps to provide cluster-wide runtime management for streaming jobs in ByteDance Cloud. It features three components: control plane service, runtime management trigger, and global storage. The control plane service is stateless and can be flexibly scaled to multiple parallel control plane instances. Streaming jobs can be configured with runtime management triggers to request runtime management on demand. The global storage manages control plane required state, such as metrics and job configurations. It decouples the periodic metrics report and runtime management enforcement. All modules can natively interact with Kubernetes and run in containers. We then present the parallel runtime management workflow overview of StreamOps. First of all, streaming jobs can request for runtime management independently. The first step is to trigger the runtime management on demand. Then, a distributed load balancer service will forward requests to parallel control plane instances for handling the request. Subsequently, control plane decouples the runtime management enforcement in three steps. First, the metrics management relies on a stable time series metrics store service in ByteDance. Streaming job related metrics will be reported to the store periodically, and the metrics retriever in control plane can query subsets of metrics according to different control policies. Second, All control policies are extensible and follow a detect, diagnose, resolve paradigm to explore runtime optimization opportunities for streaming jobs. Each control policy can also expose control settings for streaming jobs to fine-tune behaviors according to their stream processing scenarios. Third, the reconfig executor encapsulates predefined dynamic reconfiguration mechanisms to adjust resource workload configurations. For those reconfigurations that are temporarily unsupported, the executor can also fire alarms with diagnose insights to owners of streaming jobs for manual update. Inspired by research works proposed recently, we implemented 3 control policies: autoscaler, straggler detector, and job doctor to resolve common runtime issues such as processing lag and runtime failures in ByteDance. Processing lag is mainly caused by under-provisioned resources or load imbalance. The load imbalance can be further caused by stragglers or data skewness. The processing lag can be handled effectively with the 3 proposed control policies and the carefully designed models, while the job doctor is extended with a set of diagnosis roles to further handle frequent runtime failures. More detailed model descriptions can be found in our full paper. The results are remarkable. We deploy StreamOps with 40 instances in our in-production environment and measure its overview scalability. The results have shown that our system can handle up to 33K runtime management requests on a daily basis, and 99% of runtime management requests can be responded within 1 minute. We also evaluate the effectiveness of the autoscaler by configuring it for an in-production streaming job. The results show that our system can adapt parallelism of the streaming job according to the changes of the input rate. The effective autoscaling helps streaming jobs avoid processing lag and save up to 60% of CPU resources. Similarly, our straggler detector can also identify stragglers in streaming jobs by carefully analyzing runtime status of parallel tasks. Then it migrates these stragglers to healthy machines to mitigate high processing lag. The job doctor is widely utilized, with thousands of runtime management requests triggered via the dashboard per day. And we measure the number of encores requested after users have used job doctor for runtime issue diagnosis over 7 weeks. The results have shown that job doctor can help users resolve runtime issues effectively, where the actual number of encores is up to 4.5 times lower than the number of runtime issues incurred daily. In summary, this paper presented the problem that the complicated stream processing scenarios in ByteDance require cluster-wide runtime management. And we designed StreamOps for managing cluster-wide streaming jobs in ByteDance Cloud. It is designed as a standalone control plane and applies runtime management through per job triggering on demand, and leverages a global state storage to decouple the matrix collection and runtime management enforcement. We show that StreamOps can handle up to 33K runtime management requests per second, and 99% of requests can be responded within 1 minute. The 3 general purpose control policies can effectively resolve common runtime issues for streaming jobs, such as processing lag and runtime failures. That's all for my presentation. Thank you.